All right, we are still in Chapter 7, Applications of Integration. We are on packet part G. This topic, it's not directly covered on the exam as stated by College Board, the shell method here. But if you understand it, even though the question is not intended for shell method, it could be easier from time to time. So I figured we should be talking about it. In the past, it was included, but recent changes to their curriculum has dropped it from being expected to be on the exam. So just as with the disk method, all right, so I'm looking at the top image here. So you can see they've got their representative slice, and they're going to be revolving that representative slice around the x-axis. So now my representative slice is parallel to the x-axis and not perpendicular. So when you do that, you end up with the lateral surface area, all right, of a cylinder, right? You do not have the area of the circles on each end, you just have the sides. So if we take a different representative slice and wrap it around, it'd be like an onion, or if you've got a stack of papers and you roll it up in your hand and have them connect, every piece of paper there is representative here of that representative slice, and together, collectively, they make the volume of the figure. So when we're looking for this, right, we're going to have the volume of our cylindrical shell. That's why they call it a shell method, because it's almost like a seashell in terms of the layering. The volume is 2 pi, my radius, my height, my width. You're thinking of, right, 2 pi, my average radius, my height, and my thickness. Well, the average radius is going to change over time, and then we're going to use the integral to change all those radii and add them all up collectively. So the process we're really thinking of here, right, our volume is going to go from A to B of 2 pi h, 2 pi RH, right? That's kind of what, right, if you're thinking your surface area of a cylinder, right, you've got your 2 pi RH plus 2 pi r squared. All right, we just do not have the circles on the end, right? This is our area, right? If we integrate area, and then we would have, and this could be a dx or a dy. If we integrate our area, then that's how you get your volume, right? We're going from that two-dimensional space to that three-dimensional space. So if we have a horizontal axis, right? So if we have a horizontal slice and we're going to revolve it around horizontal axes, right? You're going to have your cylinder essentially on its side, which means you have a dy slice because it's going to hit the y-axis, right? You're cutting it in y slices. If you have your vertical slice as shown below, that would be a dx cut, and then we're going to be revolving that around some sort of vertical axis, not always the y-axis. We're going to have different shifts like we did before as well. All right, so then we'd have a dx here. And they have the function notation here for your heights and radii because you don't know what you're going to have, but it's got to all be in terms of x. You're going to be factoring out your 2 pi either way in either expression. But as long as you have the idea of 2 pi RH, you're going to be just fine. All right, so over here, this is key. Like I would be starring this, right? All kinds of highlighter here. This is the true difference. How do I know if I'm doing a disc washer versus the shell method? Well, the washer is going to be perpendicular to the axis of revolution. That's what makes that circle. All right, so going back to the image above, right, we have our dx slice here. Let's change colors here to blue. If I have my dx slice and I revolve it perpendicular to the axis, right, it's going to make that solid disc. But revolving it parallel to my axis of revolution makes the shell method. So if we're parallel to our axis of revolution, the shell. If we are perpendicular, it's going to be that disc method. If you draw a representative slice, it'll be a visual cue for you to know which one's which. All right, so directions say use shell. All right, so we've got to use the shell. If it does not say, if it just says find the volume, you can pick. And that's where some of the struggle is going to be in that decision making. All right, so they have our representative slice drawn. They have our image here. We're going to revolve it around the y-axis. So if I revolve that guy around the y-axis, that's my top portion, right? There's my other vertical slice. I can see I've got a shell method. So I'm thinking my volume is going to go from A to B, 2 pi RH. It is a vertical slice, so I know it's a dx. It looks like I'm going to go from 0 to 1, right? Because I'm looking at the x-axis, not the y-axis. And 2 pi is going to stay put. My height is dictated by the function, right? That's what told me where to stop. And my function is 1 minus x. And my radius, let's zoom in here a little bit. Right, if I'm centered here at the y-axis, for my center of my circle, my radius is dictated by where my representative slice is, right? So if I chose a different representative slice, all right, it's going to come out a little bit longer, so that radius is going to be different. So that radius is x away from the origin. So since we've got a dx slice here, then our radius is going to be an x dx. Again, we've done the integration. We can factor out 2 pi. We can do the power rule backwards for integration. I just really want to focus on the setup for these. All right, example 2. Again, we've got our vertical slice here. Right, we're going to be revolving that around the y-axis as it's noted here. Okay, so now I'm setting up the same way. Looks like it's going to be at 2, because if x is 2, right, then y is 8, and I can see that's my point here at y of 8. So I'm going to go from 0 to 2. I've got my 2 pi RH. Again, it's a vertical slice, so it's a dx cut. 0 to 2, 2 pi. And again, my radius is going to be x, just like it was in the last example. It's going to be pretty common, so don't be surprised by that. And now my h, it's not the distance from the function, right, because I'm stopping here at 8, and I'm stopping at the function. The function is actually my bottom piece. So if I go with my top minus my bottom, as we've done earlier, that's going to be representative of my height. So my top is really 8, and my bottom is the function. And again, we're dx. And again, we can factor out to 2 pi, we can distribute, we can add our like terms. It'll be a power rule problem, and that's all right. All right, example 3. So now they're not giving you the diagram. They're just giving you all the pieces here. So y equals 0, x equals 1, x equals 2, and then square root of x. All right, so if we have to use all of those as fences for our yard, then the only section that's created is this red section that I've highlighted. And I've got to go back and read the directions to see where they want me to revolve this around. All right, generated around the y-axis. Okay, so now we're separated from the y-axis. So if I just take a representative slice here, and I revolve that around the y-axis, right? So even if I take this slice furthest to the left and revolve it, right, there's going to be a hole in the middle, which is fine. It's all right. It's going to be like a glass, right? If you actually look at a glass, it's concave on the inside to hold the water and to give some support to the actual drinking glass. All right, so that's what we're looking at on this side. So no big deal. We got dx cut, starting from 1 to 2, 2 pi RH dx. So from 1 to 2, 2 pi. So now my r it's still going to be a random x. It's going to go between 1 and 2, but that 1 and 2 is already dictated by my upper and lower limit. So don't overthink that portion. Okay, so my r is still going to be dictated by an x. It's essentially because we're revolving around the y-axis. So when we start, we're starting there. So if we shift over and revolve around like x equals 5, then that's where the shift is going to occur. And now my height is dictated by the function. So my function is just x squared. All right, so the shift away from the origin is just affected here by our upper and lower limit. All right, pretty good setup there. So now we've got, so we know this guy's going to be decay, right, exponential decay. So if x is 0, we're at 1, right, and we know we're going to be decaying closer and closer. How close, I'm not really sure, but It's going to get smaller. I've got y equals 0. I've got x equals 1 and x equals 0. So we're looking at this section here. We're still revolving around the y-axis. So take your representative slice. Revolve that representative slice. Okay, so now we're going to go, my volume is going to go from 0 to 1. We've got a vertical slice, so you know it's a dx cut. 2 pi r h. So again, my r is just x, because our axis didn't move. And our height there is going to be our function. All right, example 5 here. All right, so we could try to graph these by hand, but in the end, we are really concerned with where they intersect. So let's just set them equal to each other first. We'll find those intersection points, and then we'll think of the parts of the graph here, and then we'll know which one's top and which one's bottom. All right, divide everybody by a 2. X minus 4, x minus 2. All right, so they're going to be intersecting at 2 and 4. So if we take these values and put them in just to get a ballpark here. So if I evaluate at 2, I got 4. 4 minus 12 is -8. -8. And 10 is 2. So then I've got 2, 2. And then if I put the 4 in, then I've got 16. 16 minus 24 is -8. And I got another 2. All right, which leads me to believe that we're going to have our axis of symmetry right down the middle. I can see that one of them is going to be concave down and one of them is concave up. All right, so then if they're going to intersect, right, I'm going to have one of them, and I'll do this guy in blue, right? So we're going to look something like this because they've got to intersect. So then I know my volume then is going to go from 2 to 4. I've got my 2 pi r h dx cut. Again, I'm revolving around the axes here. So if I take my representative slice and I revolve around the y-axis, all right, since this is my axis of revolution, my representative slice is always going to be x away. Now my height is going to be top minus bottom. All right, so I'm going to have to probably erase and give myself some more room. So my top is my red function. So we're going to go red first. Minus the bottom, which I had as my blue function. Dx. And again, we'd clean up all the pieces. We would be able to integrate that. We feel pretty good. All right, example 6 through 9, use the shell method around the given axes. All right, so now we're going to go with y equals 2x. So I've got up 2 over 1, up 2 over 1. I've got x equals 0. And then I've got y equals 4. All right, so in our representative region then, I'm going to draw a representative slice. All right, they want me to revolve around the y-axis. It's good because that means it's a shell technique. All right, so then my volume is going to go from 0. So I can see we intersect there at 2x of 2. So I've got my 2 pi, r again is x. My height then is going to be my green top, which is 4, minus my blue bottom, which was 2x dx. And again, the integration is power rule backwards. We're putting in zeros or ones and zeros and twos. We should feel pretty good about those. Y equals square root of x. And then right, if we were over here at 4, it would be at 2, just to give myself a goal here of how to do that curve better. Y of 0, and then x plus y is 2, so then y is negative x plus 2. So I'd start at 2, down 1 over 1, down 1 over 1. All right. So then my representative slice, and then revolve around the x-axis. So if I go my representative slice around the x-axis, it has to be parallel because I want us to use shell technique. So now I've got to use a dy, which means I want to solve this one for x and not solve it for y. All right, so now I'm thinking y's. All right, so I've got to almost overwrite my y's here. So I'm starting y of 0, and then I'm going up to y of 1, 2 pi, and revolving around the x-axis. So my radius is now a y instead of an x, but it's still the axis. There's no shift, no translated axes, as they say. My height is going to go from thinking right to left. So from red line to purple line, right? You may think you're going to go to the origin, but that's just the center. That's just the axes. Right? My representative slice went from red line to purple line. So then I've got to make sure I write it that way. So then I've got red line. Oh, I want to put that as a y. I drew my x a little bit too long. I'm like picking the wrong eraser. So negative y plus 2. All right, top minus the bottom, which is purple. And the purple is its square root of x, but I don't want to put x's in there. So I got to come over here. If y is the square root of x, that means that y squared is actually x. So then we're going to put in a y squared. All right, close off that parentheses, we give our dy notation. Same, just different letters. Still going to be a power rule technique, still a lot of factoring, still a lot of like terms. All right, a couple more. So now we're going to go around the x-axis here. We're going to be in quadrant 1. And if we're going to go around the x-axis, then you're thinking I want a dy. If we're going to go around the y equals 3, same, you're going to have a dy because those are both horizontal axes. So you want a horizontal sliced if you're going to use shell method. So that means I want to have x is equal to 9 minus y squared as my function. So if we're in the first quadrant, and let's say that y is 0. If y is 0, then x is 9. Okay, so then we're on the axes. If x is 0, then y is positive or negative 3. Okay, so then we have our quadratic opening down there. All right, but we want to be in the first quadrant, and we're going to revolve around the x-axis, okay? So that means that this bottom portion here, right, we don't need that part because our bounds are in the, I guess it'd be symmetric, but let's just take the one in quadrant 1. So there's my representative slice. I'm going to revolve that guy around the x-axis. Revolve that guy around the x-axis. All right, so then I've got my volume is going to go dy. So if I'm going to go from 0 to 3, 2 pi, y is my radius, and then my height is dictated, right minus left. So my right side is dictated by the curve, and my left side is dictated by x equals 0. So then it's just really the curve because I'm going to come back to the end all the time. So then I'm going to have my 9. I've got to change it to the pen again. My 9 minus y squared, and then dy, right? So if I take this representative slice, it's going to create the mirror image. If you took the bottom in quadrant 4, I understand it has the same border. You're going to have the same result in the end. All right, and now along the line y equals 3, so this is a different style here. So let's highlight our axis of revolution. we're going to want everything to be x equals, so we have x equals 5. Okay, we'll draw that guy in. Y equals 0, we'll draw that guy in. All right, so then if we solve for x here, I'm going to have y squared plus 1 is equal to x. If we graph it the way it is, just to make it graph a little easier, so at 1 is like our 0, so then like at 2 is our 1, so at x of 5, we'd have 5 minus 1 is a 2. That's why they kind of went out to the 5, I think, so you can get an idea where your curve is. All right, we're going to revolve this around y equals 3. So if I get my representative slice, now I got to revolve it around y equals 3, revolve it around y equals 3. All right, so now we got to translate it axes. Now our radius is different. So I've got my volume, right? Okay, so we're going to go from my y, right, goes from 0, and then my y is going to stop at 2, because that's all the representative slices I could have, right? This is our region. I've got my 2 pi r h dy. All right, so then my radius is dictated, right, from the center, the axis of revolution, to my representative slice. All right, so then you're going to do the same thing. You're thinking top minus bottom. All right, so my top is 3, and my bottom is my representative slice, right, which is going to be dictated by my limits of integration, which is using my function, which is y squared plus 1. All right, my height is going to be, all right, there's my height of my cylinder. So that is the length of the representative slice, right? So that's from right to left here, right? My furthest to the right is going to be 5, and my furthest to the left is going to be the function. All right, so then I'm using the function twice, so I don't actually like that. All right, so I said when I use this, I said I'm using the function, but I'm really not using the function. I'm using that value, right, that I'm going to be applying for my upper and lower. So since I'm applying that value for my upper and lower, it's not the function, it's the y value, it's that radius value, right, that we just had to move. So that's just a straight up y, that's not the function. And this is a dy. Make sure I got all my, right, because if we were revolving around the x-axis, it would be just a y as my radius. We moved it to revolve around 3, so a 3 has to be adjusting our original radius of y. Our height was starting at 5, and it's stopping at our function, and our function is dictated by y squared plus 1. All right, I think I like this one. And that's it for this one. G is done.